Welcome to the presentation. My name is Mikołaj Baczyński and I will be introducing the idea of building vacuum propeller, pushing against a quantum foam. I will introduce the theoretical basis that, in my view, allows for building vacuum propeller, describe three types of experiments to validate the idea, and analyze the test results. To see how pushing against a quantum foam could be possible, let's consider the trajectories of particle-antiparticle pairs in non-uniform magnetic field. With the strength of the magnetic field varying as shown, positive-negative pair would be pushed with a different force than the negative-positive pair because the strength of the magnetic field increases along the trajectory of the positive-negative pair and decreases along the trajectory of the negative-positive pair. Given that Fa is larger than Fb, we should expect a force acting on the magnets. The order of magnitudes of the force should be expected to correspond to Casimir force. When I was trying to formulate Ty function, I couldn't find answers to the following questions. What is v, pop-out velocity in quantum foam? Is it Planck length divided by uncertainties delta t? What is particle-antiparticle density at a given moment? As a result, I have decided to focus on experimental validation. One more thing to notice is that moving the magnets would encounter resistance, and that would allow for building the vacuum propeller. The thrust force depends on field geometry. As demonstrated here, only the y component is useful to the operation of the propeller, and the resulting force may be higher despite having lower gradient of the magnetic field, because of, in this case, if we look at the y component only, Tb is larger than Ta. Is there any supporting experimental evidence for my claims? I can think of two: dynamical Casimir effect and extraction of vacuum energy performed by Garrett Model from the University of Colorado. There are three types of experiments that can be used to validate or falsify the idea. Beam balance, I find it least convincing. Varying the magnet configurations can account for the interaction with the Earth's magnetic field. Torsion balance, I find it more convincing. Perhaps it would allow us to quantify the effect, at least at an engineering level. However, it is very difficult to compensate for the interaction with the Earth's magnetic field. Extraction of vacuum energy gives definite proof. However, this experiment is feasible only if it's possible to 100% shield the setup from the Earth's magnetic field. Also, T is very small and may not overcome friction. Let me describe the setup for the beam balance experiments. We have a laser located roughly 5 meters away from the screen, and the magnets are attached to the beam roughly 1 meter away from the pivot point. We have two forces that are due to the interaction with the Earth's magnetic field. One is acting on the base magnets and the other one is acting on the single magnet. And if the force Fe2 is smaller than the resulting thrust force, we will see positive results. There are two test configurations: positive bias configuration, in which interaction with the Earth's magnetic field is more likely to result in false positive outcome, and negative bias configuration, in which interaction with the Earth's magnetic field is more likely to result in false negative outcome. Either configuration can have push-down setup, in which the expected force is acting down on the beam, or push-up setup, in which the expected force is acting up on the beam. Positive versus negative bias configuration needs to be confirmed by testing with the number of base magnets set to 1. Here are the test results. The tests were performed in two setups: push-down setup, which is composed of base magnets, gap and bottom magnet, and push-up setup that is composed of the top magnet, gap, and base magnets. The results we can interpret as follows. First of all, by setting the number of base magnets to 1, we can determine whether the setup is positive bias or negative bias, and by seeing the results being consistent in both cases, we can determine that both setups were negative bias configurations. Looking at the results, we would like them to be correlated between push-down setup and push-up setup. We can see the correlation in green. It's like 50-50. In yellow, we can see the results that are not correlated, however, they're positive. Again, 50-50. So it's difficult to say that it's perhaps all positive. However, we can look at the results and conclude that the results, that the force depends on the field geometry. In order to confirm my assumptions, I ran simulations using FEM software. It provides 2D modeling, which is sufficient. It provides confirmation about the interaction of the forces. That is, if the simulation results agree with the tests that indicated the existence of the T-force, then that force could not be resulting from interaction with the quantum foam. Free software has limitations. One of them is that the rod connecting the magnets could not be simulated. It was easily overcome by defining a region over the magnets and integrating the forces over that region. The boundary was set to 250 millimeters, and push-down setup and push-up setups had to be placed at different locations. The bar magnet simulating the Earth's magnetic field had its coercivity set to 47.7 amps per meter. However, if I was to increase the coercivity of the magnet simulating the Earth's magnetic field, both setups could be placed at the same location and aligned according to the geographical latitude. Increasing the coercivity of the bar magnet simulating the Earth's magnetic field 100,000 times makes the simulation qualitatively closer to the tests, and here is why. Because only the lines closer to the beam magnets are affected, and away from the beam magnets, in both cases, the lines are unaffected. That means the beam magnets have little effect on the Earth's magnetic field miles away. Field analysis with the example of push-down setup with 2 base magnets and 8 mm gap shown here confirms the assumptions that I made for the beam balance test. Important things here to note is that it is not the difference between the strength of this magnet and this magnet. It is important to have these lines parallel for as long as possible, and the range variance of the magnetic field very closely resemble range A. Range B is not as efficient because it's less of the going down area. However, the main conclusion here is that basically it's all about field geometry. Let's look at the results. The force acting on the beam was obtained by integrating forces over a region of integration, and this is the region of integration, and converting those forces into 1 millimeter of delta H equals roughly 100 micronewtons. However, due to the limitations of the FEM software, the simulation results can only be qualitatively compared with the tests. The sign of delta H is expected to follow the single base magnet results, and simulations confirm the important role of field geometry. Closer look at the results. You see the results of the single base magnets, the negative here, and the same sign for all other results in the push-down setup. For the push-up setup, the single base magnet test results are all positive, and all other tests are positive as well. We can perform dual configuration beam balance experiments and compare with the single configuration beam balance. We would expect T-force to be doubled and the influence of the Earth's magnetic field totally compensated. However, one of those configurations may exhibit positive bias. In order to confirm configuration bias, I've performed tests with the single base magnets, and I would expect the following results. For the negative bias configurations, push-down setup, I would expect H push minus H pull to be negative, and for the push-up setup, I would expect H push minus H pull to be positive. The results I got for the push-down setup are all negative, which is consistent, and for the push-up setups are mixed. That means that push-up setup is inconclusive and there's no point of performing tests in that setup. Push-down setup, it may be worthwhile performing tests in that setup. The test results look encouraging. However, there is little correlation with the single configuration tests, and that is why the results need to be discarded. Moving on to torsion balance tests. These tests need to be performed with different starting angles, in different magnet configuration, NS-SN, SN-NS, and we can analyze the forces in 2D because the size of the balance is much smaller than the Earth's radius, and the forces that we have are twisting forces, which is magnetic moment plus the force T that we're expecting to find, and push forces, which are much smaller than the twisting forces. And if all the tests in all possible configurations are positive, we have a confirmation. There are two beam configuration options. Setup A, in which we have NS-SN on one end of the beam and the same configuration on the other end of the beam, or NS-SN configuration on one end and on the other end SN-NS configuration. In the case of setup B, we have to notice that FB2 has the same direction as the T-force and FB1 has the same direction as the T-force. That means setup B is always false positive. In the case of setup A, if we have FB2 minus FB1 being less than 0, that results in false positive. Also, if FMD is FM1 minus FM2, FM1, FM2, if that difference is less than 0, it is also false positive. The following conditions must be met. FBD plus FMD must be greater or equal than 0. Of course, we would like it to be equal. And the T-force must be greater than 0.5 times FBD plus FMD. Let's move on to the force analysis. Looking at the forces acting on a bar magnet in the Earth's magnetic field, we can distinguish 2 points. Theta equals 0 and theta equals 180 degrees. In both cases, the torque acting on the magnet is 0. However, the value of work, meaning potential energy required to keep the magnet at a given position, we have for the theta equals 0, the 0 value of the work, and for theta equals 180 degrees, we have the maximum value of work, meaning theta equals 0 is a stable position, and theta equals 180 degrees is an unstable position. And we have to make sure that in all our tests, 180 degrees position never happens. Looking at the NS-SN test setup, and for simplicity, assuming linear analysis of the forces due to the interaction with the Earth's magnetic field, we see that they all add up to 0. The work, meaning the potential energy, is constant. However, for practical applications, we need to consider cases where these forces are not balanced. In real life, we may have two situations. Situation in which FB1 is greater than FB2, and the situation where FB1 is smaller than FB2. We can ignore FM1 and FM2 because FB1 is so much greater than FM1. Okay, so in this case, where the FB1 is greater than FB2, we would have positive bias range and negative bias range. And the opposite would be for the case where FB1 is smaller than FB2. You would have negative bias range, and the positive bias range. Tests were performed based on beam balance results with 3 base magnets and 1 mm gap. We have pictures showing starting angle of less than 0, roughly about 0, and greater than 0. The tests were performed with the beta 1 of -75, -40, -5, 40, and 75 degrees. For -75 degrees, we see the beam is tilting entirely to the left. The R angle is negative. For -40 degrees, the tilt is to the left with some tilt to the right. For -5, the fairly even with the tendency of going to the left. From 40 degrees, they're pretty much even. And for 75 degrees, the tilting is mostly to the right. Tilt to the left is very small. It looks like the FB2 plus M1 is stronger than FB1 plus M2. However, we see positive results in the negative bias zone, so let's take a closer look. Having positive results in the negative bias zone would suggest that the T-force exists. However, we have to consider this situation. When you have this beta 1 angle close to 0, one set of magnets is in the very stable position and the other set of magnets is in very unstable position. That leads to oscillations. So we have to find a different way of testing. We can perform comparison tests. In those tests, we have 3 setups. NS, which is a setup that we use to calibrate the test. Setup R, where we expect the beam to turn to the right, and setup L, where we expect the beam to turn to the left. We construct those setups by moving entire magnet configurations from one end of the beam to another. The test preparations are as follows. We have to establish equilibrium point for the NS configuration, meaning beta 1 equals 0. For setup R, we place the stopper where the NS configuration starts turning to the left. And for setup L, we place the stopper where the NS configuration is starting to turn to the right. The rotation stopper must be placed so that the NS configuration does not move, yet the torsion wire is exerting minimal force against the T-force. So, moving on to the results. By comparing the L and the R setup results, we ensure that the effect is not caused by FB1 plus FM2 being greater than FB2 plus FM1 or vice versa, and we are eliminating oscillations caused by 180-degree angles between the magnets and the Earth's magnetic field. If you look at the results, we have achieved 100% consistency between the L and the R setups, and most of the results are positive, and that's very encouraging. We can also perform single set configuration tests where one of the magnet configurations is replaced by a non-magnetic weight balance. In those tests, we have 2 steps. Step 1 is to determine beta 1 of 0, means the 0 angle position, and in step 2, we put a rotation stopper at beta 1 slightly higher than 0 so that the single magnet is not in the unstable position. And those tests, if you look at the results, are very encouraging. However, if the ratio of FB1 to FM1 is too high, we may not see positive results at all. However, for the number of base magnets of 2, we see that the results are positive. After performing the tests and running the simulations, my conclusions are as follows. The beam balance test, the interaction with the Earth's magnetic field is constant within the beam movements. They're less sensitive than torsion beam tests, and dual configuration tests didn't show compensation of the forces due to the Earth's magnetic field. The torsion beam tests, the high sensitivity can introduce errors, and interaction with the Earth's magnetic field varies with the twist angle. that it is impossible to measure the T-force reliably. Both tests and the simulation suggest that the T-force does exist, and the strength of the T-force depends on field geometry. This is the page that contains the results of all the tests for comparison, and based on those tests, in my opinion, it is worth further investigation. That means it is worth building a lab that is 100% shielded from the Earth's magnetic field. Going even further, here's how I see the Propeller's prototype being built. We take the magnet arrangements and tilt them like in a windmill and rotate the blades. That means pushing against quantum foam. However, I don't expect this to overcome Earth's gravity. And finally, here's my call to action. I'm looking for help, collaboration in vetting the theory, vetting the tests, testing in a shielded lab, and building the device. Thank you all for your attention, and I'm looking forward to hearing from you.